We're going to talk about the mechanism, another aspect of the mechanism of E2 reaction. It turns out that this reaction is not only regioselective when we have different bases, but can be also stereoselective, or stereospecific rather. So let's look at the mechanism. Remember that this is a concerted process, and that means that at the same time, we're going to have a proton transfer. So the base attacking to get a beta hydrogen, remember that. And at the same time, we're going to have the loss of that leaving group. That's what's happening. So let's look at one structure. In this time, let's do this. Yeah, I'm going to have an H here, that's a metal. And here I am having hydrogen, metal, and here I'm gonna put here wedge. So that is an ethyl group. So what we see here, the mechanism for this reaction is not only concerted with that, but by, say, experimental evidence, looking at the structure of the product, it has been determined that this mechanism happens through the anti-periplanar configuration. What is anti-periplanar is like opposite sides. So the beta hydrogen needs to be opposite to the leaving group. These two opposite. This is what we have here. It's hydrogen, so pointing opposite side. Now to see that, we can say if we have a base here, what do we learn? That we'll learn, so the base will get a proton here, and then you will do this in concerted fashion, and you will form an alkene. This time, remember we're making, this is this double bond, and now you will have hydrogen, metal. I'm going to do this so that you see better. So here you will have wedges, here you have an ethyl and a metal. Now, a good, say, very useful way to do mechanism in predict products when we're doing E2 reactions is using the Newman projection. This one here is the wedge and dash. And now, what I'm going to be doing, a Newman projection of this one, and I'm going to imagine that this is my eye. So I am here. So, and I see, so this circle will represent that carbon, this one here, which is actually, that's your alpha carbon, that's beta. All right. And of course, that's a beta hydrogen. So I am here then pointing down, you have hydrogen, and then to your right side, you will have an ethyl, and this in the wedge is a metal. And right opposite when you look at the Newman, alpha carbon is in the back, right opposite you have a bromine, and then to your right side you will have a metal, and to the left side you will have a metal. I think I'm missing some, oh, yeah, to the right side, that's a hydrogen. So yeah, so you will have hydrogen to your left and metal to your right. And so for the mechanism, again, these two need to be anti-periplanar. This is what we just did. They need to, when you have this type of drawing, make sure that you have the beta hydrogen opposite to the leaving group. If it's not, you can rotate it. You need to rotate it so that they are opposite. Now in this case, we have this. Now the base is attacking here, getting the hydrogen. Now the pair of electrons is going to make a double bond between the beta carbon in the front and the alpha in the back. And what happens now, we're gonna draw what remains after that. So in the front carbon, I have an ethyl here, I have a metal, and in the back carbon, after the bromine is gone, you will have a metal. In here, you will have a hydrogen. Now this is this way. So remember that here in the Newman projection, here the carbon here in the front is eclipsing the other. This is exactly what we have here. Now I need to redraw it, and what I'm going to do is go from here to this position. When I do that, see in the carbon in the front, I have an ethyl and a metal. For the carbon in the back side, I have a metal and a hydrogen. So notice this is the same product. So what we need to see here is that you have metal, metal, opposite sides, ethyl and hydrogen, opposite side. So that's a good way to predict products. So if you find it easier doing wedge and dash, it's fine. Otherwise, I'll say that most of my students actually prefer to do the Newman projection. If you learn how to do that, it's very easy, because you may see in a problem that you're not given that specific conformation. So you need to go and put it the beta hydrogen opposite to the leaving group. And so this is important because this is the only product observed. So in other words, I'm going to draw the other product. The other that is not formed will have, say, metal, and here ethyl and hydrogen. That's not formed. So this reaction is then gives you a specific stereoisomer. So it is a stereospecific. And here, just to remember things, let's look at that. This particular, let's do the EZ. So at this carbon, this has higher priority. The ethyls, I'm going to do number 1 and number 2 here. And in the other carbon, the metal has higher priority than the hydrogen. So as you can see, the two highest priority are to the same size. So this is the Z isomer. This reaction will give you specifically that isomer.